Dear students, good morning. First of all, I would like to welcome you all again in the MSc final class. I have already discussed about the properties of nucleus, and in today's online class again I will discuss another property of nucleus, that is nuclear spin or total angular momentum. Angular momentum of a nucleon can be described as spin angular momentum and orbital angular momentum. So let us first discuss the spin angular momentum. Each nucleon, whether it is a proton or a neutron, has spin angular momentum magnitude small s equals to under root s plus 1 h cross equals to under root half plus 1 h cross equals to root 3 by 2 h cross, where s equals to 1 by 2 is the spin angular momentum quantum number. Each proton and neutron are fermions with spin quantum number s equals to half. And next is orbital angular momentum. The magnitude of orbital angular momentum can be expressed as magnitude small l equals to under root l plus 1 h cross, where l is orbital quantum number. So the total angular momentum is the sum of spin angular momentum and orbital angular momentum, which can be written as the magnitude of the total momentum of the nucleon is capital J equals to under root j plus 1 h cross. The net angular momentum of the nucleus is the resultant of all the spin angular momenta and orbital angular momenta of its constituent nucleons. The magnitude of the nuclear angular momentum due to all nucleons is magnitude capital I equals to under root I plus 1 h cross, where I is called the total angular momentum quantum number or nuclear spin, which may be an integer or a half integer. Greatest possible component of the total angular momentum along any direction is capital I z component equals to mi h cross, where mi can take values 2i plus 1, which varies from minus I to plus I, where mi is the magnetic total angular momentum quantum number. The word spin usually refers to the resultant angular momentum of a nucleus in nuclear physics, whereas in atomic physics the word spin refers to the intrinsic spin angular momentum. It is found that nuclei with even Z and even N have the total angular momentum 0 because pairs of protons are formed in such a way that their angular momenta cancel, and similarly pairs of neutrons are formed in such a way that their angular momenta cancel. The total angular momentum quantum number capital I is integral for nuclei with even mass number A and half integral for nuclei with odd mass number A. The whole following conclusion about total angular momentum of a nucleus can be made. Here in this table you will see this is the mass number, which can take either even or odd values, and in the second column, that is proton number, third column is neutron number, and the last column represents the nuclear spin capital I. So if proton number Z is even, mass number again is even, so it is even. Neutron number, if even, it is even. It means if all three values, mass number, proton number and neutron number, if all three values are even, the total nuclear spin I will be 0. The same thing can be considered for odd proton and odd neutron numbers, whereas if mass number is even, then the nuclear spin comes out 1, 2 or 3 or other values it can take. In the same way, if mass number is odd and proton and neutron numbers both are even and odd respectively, the nuclear spin will be half 3 by 2, 5 by 2. And similarly, if mass number is odd and proton and neutron numbers are odd and even respectively, the nuclear spin will be half 3 by 2 and 5 by 2 and so on. Now I come to the next property of the nucleus, that is parity. The parity of a wave function psi is related to the symmetry properties of the wave function psi. That is, if magnitude psi vector r square equals to magnitude psi minus r square, means if the position of a wave function is inversed uh, in such a thing, what happens about the wave function. So here we have considered psi r equals to plus minus psi minus r. That is, if the spatial part of the wave function of a nucleus is unchanged when the space coordinates are substituted by minus x minus y and minus z, that is psi minus x minus y minus z equals to, if it is psi x y z, that is wave function is invariant under reflection, that is function is symmetric as regards spatial inversion, then system is said to have even parity. If the spatial part of the wave function of a nucleus changes sign when the space coordinates x, y and z are substituted by minus x minus y and minus z, that is psi minus x minus y minus z equals to minus psi x y z, then system is said to have odd parity, that is function is antisymmetric as regards spatial inversion. That is, if we invert the spatial components, if the sign of the wave function changes, it means your wave function is antisymmetric, and if the sign remains same, it means the wave function is symmetric. These two equations, equation 7 and equation 8, may be combined in the form of some operator, that is in the form of operator. These both equations can be represented as psi minus x minus y minus z equals to p psi x y z, or it can be written as psi minus r equals to p psi r, where p can take values either 1 or minus 1. If p equals to 1, it corresponds to even parity, means this parity operator is positive, and if p equals to minus 1, it corresponds to odd parity, that is negative parity. For parity operator p, p psi rt equals to p psi minus rt with eigenvalues p equals to plus minus 1. Here p is your operator and it can take two values, either it can take plus 1 or it can take minus 1. So parity is associated with quantum number plus minus 1, and it is also denoted by symbol pi. In spherical polar coordinates, your coordinates are r, theta and phi, a reflection about the origin is equivalent to the following transformations. Psi, sorry, r is replaced by r, theta is replaced by pi minus theta, and phi is replaced by phi plus pi. To a reasonably well approximation, wave function psi of a nucleus is the product of a function depending on space coordinates and a function depending on the spin orientation. It has been found that intrinsic parity of proton as well as of neutron is even, that is P intrinsic nucleon equals to plus 1. It is found that parity of a nucleus in a given state is related to orbital quantum number L in the following manner: P equals to minus 1 raised to power small l. The orbitals s, p, d and f corresponds to L equals to 0, 1, 2, 3 respectively. So parity is even for even I and parity is for odd I. If R1, R2, RA are coordinates of nucleons in the nucleus and psi and R1, R2, RA represents the nuclear wave function in a state of definite parity, then psi and R1, R2, RA equals to plus minus psi n minus R1 minus R2 up to minus RA. To a good approximation, the wave function psi of a nucleus is the product of the wave functions of its constituent particles. If the nuclear particles have angular momentum quantum number L1, L2 respectively, then parity of the nucleus as a whole is the product over all the nucleons, that is given by P equals to P1, P2, P3, and this product can be written as pi I, P intrinsic I and P again PL intrinsic I, where pi L, PL intrinsic that represents uh, P intrinsic nucleon, and that is 1 for nucleon, and equals to minus 1 raised to power L1 minus 1 to raised power L2, that is minus 1 to raised power L1 plus L2, that is minus 1 to summation L1, that is summation Li is even, then P equals to 1, and if it is odd, then P equals to minus 1. The total angular momentum is generally called the nuclear spin, and it is represented by I, but it is different for the spin angular momentum. The parity of a nucleus is usually represented by a superscript plus or minus on the total angular momentum spin of the nucleus, that is Ip equals to spin power raised to parity. Spin parity state of a nucleus is completely determined by a single unpaired proton or neutron. So, as we have discussed, the kind of nuclei, that is for even Z, even N nuclei, I raised to power P equals to 0 plus, that is this represents the ground state. Inner cells are completely filled. Protons and neutrons in an even Z nucleus tends to pair off separately. For even Z, odd N nuclei or even an odd Z nuclei, total angular momentum and parity are determined by the unpaired nucleon, that is I equals to L plus minus half, that is P equals to minus 1 raised to power L, which represents the ground state, where L represents the orbital angular momentum quantum number of the unpaired nucleon. For odd Z, odd N nuclei, this parity P equals to minus 1 raised to power Ln plus Lp. Parity is important quantity in physics. Parity is conserved in strong and electromagnetic interactions, but parity is not conserved or it is violated in weak interactions. So that's all in today's online lecture. Thank you.